how there's a lot of particles. Like the standard model is not just one or two particles, it's a ton of particles, right? So I mentioned the three families, leptons, quarks, and bosons. Under the leptons, we have a different, a ton of different particles. Under the quarks, we have a few different quarks. Under the bosons, we have a few different bosons. So, it's, again, it works and it's experimentally proven and it's got experimental success and discovering these particles and how things work. It works. The standard model of particle physics is still a thing. Just because somebody finds it ugly doesn't make it go away. Okay, it's going to be a thing. It's a thing. It's progressed physics. It's given us experimental results that you can't ignore, and in fact, you need. So this person's point of view is valid in that it's not the most graceful, ties everything together and gives you a deep insight kind of story. But the fact is that you have to kind of just get over that. Until you come up with a better theory, you just have to take it, right? And that's kind of where we're headed, which is to try and get a better theory, which, by the way, is incomplete because we're going to talk about the grand unified theory today a little bit, but it's not achieved yet. They tried, and it is still a work in progress, as far as I know. I don't believe that they achieved it, okay? Worse, the standard model does not mention gravity at all. So it does not. That's the other thing about the standard model, is that it doesn't really explain gravitation. For gravitation, we do rely still on general relativity. And if you don't care about relativity, if that's sort of not a thing for the environment you're working in, then Newtonian mechanics is just fine. And so gravitation, again, when we go to school for physics, we would learn about it in Newtonian mechanics and in general theory of relativity, if you take that. If relativity is not important for your problem, then you wouldn't even learn that. So yeah, it could be that the grand unification theory is unobtainable, but for the people who were working on it, they were still very hopeful about attaining it. And even now, I would say there is still a lot of motivation, because it's kind of like you can help out with the more and more direction of particle physics, or you can do something totally different. And this is sort of the totally different, which is to come up with a completely different, additional, broader, bigger theory that will explain everything. It is difficult, though. I'm not saying it's easy. So if one tries to graft gravity onto the standard model by hand, one finds that the theory blows up. It yields nonsense. All attempts for almost 50 years to graft the quantum theory and relativity together have proved fruitless. Given all its aesthetic defects, we conclude that the only thing going for the theory is that it is undeniably correct within its experimental domain. Clearly, what is needed is to go beyond the standard model to re-examine the unification approach of Einstein. So even this person, the author of the book, Michio Kaku, is admitting that in spite of all his issues with quantum mechanics and with particle physics, it is undeniably successful. It is undeniably yielded experimental successes and results that you can't ignore. It has progressed our understanding. So you can hate it, love it, you can't ignore it, So it is something we have to learn. It is something we have to work with, and it is something we take into account. And if, by the way, if you want to challenge it and come up with a new theory, it better explain it. It better contain particle physics, right? Because how come you don't wear your ring anymore? I mean, I wear it sometimes. I don't wear it sometimes, I've not been well, so things are a little bit shifted, I guess. Still adjusting. So basically, this the challenge also for grand unification